The broadcast is now starting. All attendees are in listen-only mode.
On behalf of RBCS and software test professionals, welcome to this webinar on towards true engineering. I am Rex Black, president of RBCS, a worldwide testing and quality assurance firm. We serve clients range from small startups to Fortune 20 global enterprises. Since 1994, RBCS has delivered insight and confidence to hundreds of clients around the world. Our team of international consultants deliver customized training, consulting, and outsourcing services for companies that are looking to improve their test and quality assurance practices. I'm the author of 12 books on software testing, including the bestseller Managing the Testing Process, 4 books on the ISDQB program, and a collection of new ebooks. RBCS is presenting this webinar in partnership with software test professionals. Check out their website at www.softwaretestpro.com. Attending today's webinar may earn you credit for QAI and ASQ recertification. Check with QAI or ASQ to determine how to qualify. It typically involves saving the attendee email that you'll receive after this webinar. Attendance at today's webinar does earn PMI PDUs. I'd like to thank Bill Mays for reviewing the materials for PDU status and for making valuable suggestions. Attendees will receive an email telling them how to claim PDUs, including the PDU code. PDUs are available for live webinar attendance only. Before we start the presentation, some housekeeping notes. If you have any questions, feel free to submit them at any time. Please note that they will only be answered at the end. I'm not able to look at the questions as they come in until the presentation is complete. You don't need to ask for presentation copies. The presentation is on the web, rbcs-us.com, basic library. Navigate to the resource tab at the upper middle, and from there you will find the basic library, and you will find the posted presentation there. And by attending this webinar, you have automatically registered for the free e-learning drawing. Check your email over the next couple days and watch that spam filter. I hope you enjoy this free webinar from RBCS. We do these free webinars as a service to the software testing community because at RBCS we are a not-just-for-profit company. So today's webinar is about how we go from being a craft of software engineering, which is we currently are, to actually having a real engineering discipline. And this picture on the opening slide here is a bridge, and is a bridge that goes to Hong Kong's airport. I believe it is the largest suspension bridge in the world. It is quite a feat of engineering. And something of this size and complexity that's reliable is the product of a true engineering field, and I want to look at why we're not there yet and how we get there. So software, excuse me, software began as a profession about in the 1950s or so. You could say that it goes back a little earlier than that, but, generally speaking, this is the point where people actually started developing significant software applications for non-military purposes, and software started to move out into sort of a general use rather than just being something that was used for code breaking and targeting missiles. And testing has evolved along with it. Some people like to say that testing is dead, but it is certainly not. It has been something that's been around in one form or another since the beginning, of course, and in the form of independent test groups, something that's been around since the 60s. And it's evolving rapidly. And we can build very cool stuff, certainly. But if you look at the way that software engineering and software testing are done, it really has more in common with a craft rather than other forms of engineering. So let's look at what we can learn from other forms of engineering, some history, and what other forms of engineering have, and see how that would maybe help us make a true engineering discipline out of our profession. So first off, what do I mean by engineering? So Fairly straightforward definition here. The application of science, math, and technology in the construction of useful things. Okay? So, useful things, that's an essential part, and certainly that's something we do now. Software is useful. So we got the second half, but do we really have the first half? Science, math, and technology? Well, we have the technology, in the sense of we have the underlying silicon that allows us to do all this wonderful stuff at amazing speeds, and we've got spinning disks, solid state storage, and so forth to store the data. There's a lot of technology, without a doubt. All that technology, of course, built with a true form of engineering, electrical engineering. But if you look at the science and the math that's behind software, it's still pretty limited. We don't really have that. I studied computer science in college and got a computer science and engineering degree. Learned electrical engineering, and certainly the kind of rigor that was present in the courses that I took on the electrical engineering side of the degree really wasn't there on the software side. You didn't have all of these very precise equations that would tell you how things would behave in the real world like you do in other forms of engineering. So what we have is a process of engineering, of the very software engineering, which is very much about process. I mean, you could say that really the last 20 years or so have primarily been people fighting about process, right? CMMI on one side, Agile on the other side, and people arguing about how we do this right. What's the right process? And of course, skills is a big component, and that's what we rely on. We rely on trying to figure out what's the ideal process for building software and testing it, and rely on trying to figure out what the right skills are. And as I said, the math and the science are not something that's so much looked at. It doesn't bring on a lot of debate. Now, there's nothing wrong with craft, and you can find plenty of craftsmen out there in the world that build nice things, build beautiful furniture and stained glass windows and other nice craft kind of stuff. But that's not how other engineered products are built. They're not built through crafts. Bridges are not handcrafted. They're engineered products, if you will, assembled from components of known properties. Same thing with airplanes. We're not talking about craft. Now, of course, more and more airplanes have software in them, and so the software, becomes the weakest link. And if you caught my webinar, I believe this was last month, I was talking about software bugs that, killed people or cost $1 million or more, and one of those is a software issue having to do with the automatic pilot on a Airbus, which cut off at the most inopportune moment and created a state of confusion in the flight crew that resulted in a plane crash. So I'm not saying that every time a plane crashes it's because of software, but I'm saying that sometimes planes crash because of software. And so this craft approach is really not something that we want in safety critical, mission critical types of situations. So let's look at this for a minute and get a little bit more in detail on crafts. So early on in mechanical engineering, and one of the main forms of mechanical engineering in history has been making weapons. That's kind of what we humans are really good at, is we get some sort of technology, and instantly the first application of it is always, let's figure out how to kill other people with it. So we could have a whole conversation about what that says about human psychology, but anyway, mechanical engineering, making arms, swords, those kind of things. The practitioners of those crafts were craftsmen, and of course, and the approach used to organize the work was what are called guilds. And so a craft has elements of art in it, but it's on the path to engineering typically. And what happened in these guilds was that people would come on as apprentices, and they would be apprentices to master craftsmen, and they would learn from those master craftsmen, and eventually they would become craftsmen themselves through a whole process of learning. Now, certainly there is an element of economics here, I guess you could say, controlling entry, preventing too many people from doing it, so you'd have these guilds that would sort of enforce the limited entry into the field, and that of course has the effect of keeping prices up. But the more noble part of it was that the craftsmen were trying to make sure that people that practiced the craft actually knew how to do it right. Now, there are still crafts around today, of course, and you look at this picture here, this nicely handcrafted sword. That's an example of a kind of craft that was around for probably longer than writing. We don't have guilds anymore, but we still have crafts and craftsmen, and sometimes people apprentice and so forth. So some of that is still around. Now, interesting sort of analogy here. It used to be when you would have a sword that was used in a crime. I mean, somebody goes berserk and chops up the Burgermeister in the town square or something like that. Not only was the person punished, but the crime itself would also, or the sword itself, would also be destroyed. The argument being that it was somehow taken over by evil spirits. And you see something like that in the way software engineering works. So when the software engineering process breaks down and leads to the introduction of bugs in the software, I mean, that's just a natural process breakdown. It's going to happen. But what we see is many times the people involved, the software engineers and testers involved, get blamed. Oh, well, you guys screwed up. You guys introduced the evil spirit that resulted in this bug. So, as I said, you look at this and think about what these kind of hallmarks of craft are, and you see them present in what we do in software engineering. Now, let's move from mechanical to civil engineering, and think about the Romans. Okay. Now, I'm not talking about modern Romans. Of course, there still are Romans in the sense of people that live in the city of Rome, but I'm talking about the Roman Empire. The Romans were civil engineers of a type. They built some stuff, and a lot of that stuff is amazing. You see a picture of a aqueduct and road system here. Remarkable. Still standing. You go to Rome, you see examples of it. In fact, you go a lot of different places. You go to Bulgaria or Lebanon, and you can find ancient Roman ruins. They're not anywhere near as ruined as you might think they'd be after 2,000 years. So amazing stuff. Very useful stuff. So it's true engineering. And of course, it's just civil engineering. We're in bridges and roads and aqueducts and so forth. That's civil engineering. But where's the math and where's the science? You can't do calculus with Roman numerals, and besides, there wasn't any calculus at that point because Newton was a good 1,500 years in the future. So you had no Newton, you had no Newtonian physics, you had no calculus. So you had no way as a Roman civil engineer of understanding how what you did worked. The physics behind it, the math behind it, you had no way of understanding that. You'd have some empirical knowledge of, if we do stuff this way, it works. So we keep doing it that way. Like arches. You see in the figure here. Get the highlighter out. In the figure, we have an arch. Okay, well, that's nice. An arch there. Why does the arch work? The Romans can't really know that. I mean, they can know it intuitively why the arch worked, but they can't know from a physics point of view why the arch works. Oops, sorry about that. So, as I say, it's empirical, right? They do stuff, and they go, oh, yeah, that works. And then sometimes they do stuff, and it's like, oh, that doesn't work, so let's not ever do that again. And, you know, that was how they did engineering. They had a handful of successful processes that worked for them, and they just focused on following those, which is pretty much what we're doing when we build software. There's stuff that works, and it kind of sort of seems to work, and so we just try to do it over and over again. And we got to do it that way in order to build good software. But the process is everything. The process, following the right process, it's going to solve all of our problems, right? Well, that's craft, right? Because you couldn't explain why it works, right? I mean, people are advocates of Agile, for example. Well, why? What is it? Yeah, short feedback and, get stuff built. Well, yeah, but why? Why would that work rather than planning, right? The explanations are all about psychology, really, when you look at them, and they're not, they don't translate over to other forms of engineering. So we don't know why things work. We don't know why software works. We build it, and we notice patterns of stuff that works, and we struggle to recreate those patterns, but we don't really understand what we're doing. Now, contrast what the Romans did with the Seoul subway system. This is the longest subway system in the entire world, and if you ever visit Seoul, you just have to go down and look at this thing. It is even if you're not a fan of public transportation, it is a remarkable feat of engineering. All very, very clean, automated, amazing structure. For a myriad of reasons, the Romans could never have built anything like that. You could not build something like that using an empirical, craft-based approach. You don't have the understanding of the materials, for example, to actually construct the whole thing. You just couldn't do it. It could not be done in an empirical form. So this requires that you actually get into understanding engineering. You've got to have calculus. You've got to have physics. You've got to have mathematical ability to model things and design things. And yes, I'm talking about big upfront design here. You'd have to do that. You can't just sit down and go, oh, well, we're going to build a subway system. So why don't we start and we'll just dig a hole and we'll put a train that runs between these two places that are like a kilometer apart. And then we'll just iterate that process. And eventually, out of that, the entire subway system will just burst forth. No, that's not possible. Civil engineering is never done that way, at least not now, because you can't build something like the Seoul subway system, for example, using that approach, no matter how good your process is. So let's look at another back to civil engineering here in Romans versus modern times. Okay, so you see a picture here of of an aqueduct, Roman aqueduct, and you got a reservoir, you got intakes. Okay, that's all pretty similar to what we do now. And they knew how to, construct conduits and pipes and so forth, and dig tunnels, and so they could get the water via the aqueduct system that you see here at the upper part of your screen down to the city. Oops. What just happened here? What happened? Huh? Well, apologies for that, guys. It's my screen just kind of got weird on me here. 1 minute here. Get this fixed. Okay. Sorry about that. Okay. That was rather irritating. Hopefully you're all there. I want to take a quick check here. We have no unanswered questions. So apologies for the temporary glitch there. That was kind of weird. I tried to explain what I saw on my side, but it wouldn't make a whole lot of sense. Just all of a sudden, I didn't see the interface. So anyway, we're back. So Roman aqueduct, taking up where I left off. So we've got the Roman aqueduct here, and you see, it's taking water out of a reservoir. It's taking it down to the city. Okay, that's good. But, people got sick. I mean, for one thing, you had lead pipes, which lead's very easy to work with. It's a ductile type of material. But, usually not a particularly good idea to drink things that are coming out of lead. So you got the lead pipe problem. You got the, whatever falls into the reservoir eventually is coming out of the pipes. It's not sanitary. I mean, one of the least healthy things that you can do is go find a big pool of standing fresh water and drink out of it. Do that often enough, and something very unhappy will happen to you. Now, if you look at the modern system shown below, we've got chemicals that we're using here now to purify the water in that system, filtering out all the gunk and putting chlorine in there to kill the bacteria in it. And, it's obviously a much more sanitary, safe type of thing. And, pretty much anywhere in North America and Europe, you can turn on a tap and fill a glass of water from that tap and drink it and not have to worry about, is this going to make me sick? Now, there are other parts of the world you go to and you fill up a glass of water and drink it and something not so happy would happen to you. But, when water is processed, as shown below, using modern systems, works just fine. So, let's look at this issue of modeling that I brought up a few minutes ago. That bridge that they built in Hong Kong, you go out to the airport, which the new airport in Hong Kong, well, it's not really new anymore, but when they put it in, they built an island out in the middle of the bay and built this enormous bridge going out to it. But one of the things you have to worry about is a typhoon. You can have a typhoon come along. Typhoon just being, what we would call in the United States a hurricane. Basically, typhoon is the same thing. Cyclone is also the same thing. So the three names for the same phenomenon, depending on where they are. So, a typhoon could be a big problem for a bridge. And, the airport's on this island, so there's no way to it but with the bridge. So, typhoon comes along and blows the bridge down. Wow, whoops, airport's out of commission. That's a problem. So, as I said, you can't just build pieces of it, build pieces of it and see what happens. You've got to design it. So what did they do? They need to know, will it stand up to a typhoon? So they used models. They had a replica of the bridge that they built, using the same materials, because you can do that. You've got standard materials here, right? So they have the same materials, and they put these things in a wind tunnel and simulate a bridge, and they come up with various kinds of statistical models. It's called the Monte Carlo simulation, and they simulated the different kinds of things that could happen. So why were they able to do that? Well, as I said, they have standard materials. There's steel, there's concrete, there's cables that are going to be used, asphalt and all of these things, standard engineering materials. They could make the models out of exactly the same stuff that the whole bridge was going to be made out of, and they have mathematics that allow them to understand the behaviors of those materials as well as the behaviors of wind. You got Bernoulli's law, for example, dictates how fluid flows, including air. So they were able to do this modeling. They were able to make these predictions of what would happen. And what they've been doing over the years is when real storms happen or real problems happen with the bridge, they compare, okay, well, what did the model say would happen here? What actually happened here? And they're able to tweak the model. So they're able to continuously improve their model. We can't do that in software engineering at this point, except for certain limited situations. So, for example, you can build performance models. And I've done that. I've worked on projects where we've done that, used performance modeling to say, okay, this is how this application or system is going to behave under these levels of load, so forth. But modeling of general behavior, no, we can't do that yet. There are various challenges in the way of doing that, and until we get to the point where we are able to do that kind of modeling, then we're not going to be in a true form of engineering. Let's check something here briefly. Okay. Just checking to see if anybody's having any problem seeing the presentation here. Apparently not. Good. Got a little spooked by that whole disappearing interface thing. So let's look at this issue of materials here a little more. So we think of what's software built out of. Okay, basically it's words, right? I mean, they're languages, they're programming languages, and they are words. They're a formalized type of language, but it's language, it's words. And then the compiler is going to translate that into binary instructions that the CPU is going to execute. Okay, so that's the fundamental material that we're working with. You get right down to it. You're programming in the language, so that's what you're building with. So you've got loops and branches and other forms of executable statements that in turn get translated into various kinds of jumps and assignment statements and so forth down in the guts of the CPU. Okay, contrast that with what other forms of engineering use. So you've got steel, concrete, glass, plastics, those kind of things. And these are standard materials. Now, what I mean by standard engineering material is that those materials have properties. You don't have to, say, guess at how much stress you can put on a piece of steel before it bends. Okay, the yield strength of steel is a known thing. You don't have to wonder about what kind of corrosion will occur with a particular material. Certain metal, for example, exposed to certain types of environments. That's known. We, as engineers, people know that. You don't have to guess at, if it gets really hot, will it melt? Okay, people know everything. All these materials, they have known melting points. It's known this is the place where it will melt. And there's math underlying all of this. So you've got, you think of steel, for example. Steel has a known crystalline structure. Now, you don't think of it as a crystal, but it has a crystalline structure to it, if you will. It's how everything is arranged in a steel bar, I mean, down to the individual atoms of iron and chrome and molybdenum and all the other things that are in there. People know how that is going to behave. They know how it exists. We can't do that in software engineering yet. I mean, yes, it's not a question of a particular programming language, what will that translate into? If the compiler is built right, yes, you can, you know the zeros and ones that are coming out of that. But that's not the same as having standardized materials. You think you're driving past a bridge project, you don't see people making rebar and making concrete, like actually formulating concrete on the side of the bridge project, right? You get stacks of rebar there, they got stacks of cable, they've got concretes coming in, and it's in a big mixer, and it's all ready to go. Nor, this is pre-done stuff. The analogy in software would be that rather than building things up from instruction by instruction, you actually are building out of standardized components. And again, we don't have that. We've got some of that. We're getting towards some of that. Like, so for example, you think databases. People don't tend to build their own databases anymore. They've got, there's databases out there. But you get into the database itself, and the database itself was a hand-built thing. So we're not to that point of having the same kind of engineering materials that the other engineers have. Now, engineering is, it uses science, but it's not like science in the sense that science is a search for truth. Engineering is the building of useful things. And, engineering sometimes doesn't work. It's not just software that has bugs, right? So if you think about how bridges are built, yeah, there's math and science behind that for sure. But there is also there were failures. So in the UK, which was one of the first places to mass rail systems, when they built bridges, railway overpasses, at first they would use cast iron. Cast iron is strong until it's not, because it's brittle, so it'll shatter. And they would have instances where trains would be going over a bridge in a high wind or something like that, and the bridge would fail, and just the whole thing would fall down, and the train with it, of course. So that resulted in standardization of rules about the way to build a bridge and the materials to be used and so forth. And we are starting to see that in software engineering. So CMMI is an attempt to standardize on development process. The ISDQB program, which I'm a part of, is certainly about trying to understand good standards and processes for testing. But we are certainly not all in agreement. If you look at other forms of engineering, civil engineering, for example, there's not like huge controversy over how to build a bridge. What materials to use. That's pretty much settled. We still have disagreements about what's the right process to use to build and test software. And some people would say, well, it's too early to standardize. We need to try to, let this thing sort of ferment a little bit longer. But my take on this is that if we do incorporate mistakes into our standards now, which I'm sure we have, right, that we would correct those over time. But you have to start moving in a direction to move forward, right? If we're going around in circles, rehashing the same things over and over again, then we don't make progress. So, regulation. How do you want to be regulated? This is part of a profession. If you look at engineers, doctors, lawyers, these are really self-regulated in the sense that there are professional bodies composed of those professionals which are driving the rules. You have other professions that are, the government is more in charge of regulating, and to odd purpose sometimes. So, for example, there was a case not too long ago of a woman who was doing floral arrangements and selling them from her house, and the competing florists, I guess, decided that that wasn't okay, and they ratted her out to the government. And they said, the government just came in and said, "Well, you can't do that because you don't have a florist license," and drove her out of business. So, personally, I'm not terribly worried about unlicensed florists because there's a limit to how much damage an unlicensed florist can do, but unlicensed engineers, that's a problem. Driving across a bridge, I want to know that that bridge is properly made. So, interesting quote here from this is the National Society of Professional Engineers in the United States. It talks about how 100 years ago anybody could do this, could work as an engineer, and so licensing was introduced in Wyoming, and the professional engineering license is basically, do people know what they're doing? Do people actually know what they're doing as professional engineers? You want to drive on a bridge that was built by somebody who woke up one morning and said, "I think I want to be a bridge builder," who dropped out of high school and said, "I think I want to build bridges"? Or do we want to have some sort of program where we're able to say, look, this is the standards that we set for people to be professionals. This is what it takes to be a professional software engineer. And as I said, we're getting there slowly and not without some amount of debate, but we are getting there. Now, can we be software engineers? Could we, in the next 100 years, transform software engineering and software testing into true forms of engineering? Some people say, "Oh, it's not. It'll never get there. Can't get there." But think about this. You got 1903. All right. You see the Wright brothers there flying their airplane. Okay. You got 1961. Right. What we got here, we got, launching satellites, launching Yuri Gagarin, first man into space there. That's 1961. 1969, you got Concorde, commercial supersonic transport. 1981, you have space shuttle. So that's less than 80 years. So in less than 80 years, aeronautical engineering was transformed from being a craft, literally two dudes in a garage, two bicycle makers in a garage building an airplane, to being a true form of engineering. Now, 150 years ago, there was still debate as to whether a heavier-than-air object could fly. That was still quite a controversial statement. Somebody say, "Oh yeah, I can build a heavier-than-air object and it will fly." People would, "No, you can't. You can make hot air balloons and those kind of things. That'll float, right? Floating's different than flying, but no, you can't make heavier-than-air objects that will fly." Well, sure enough, we can. We do, and now it's a very sophisticated form of engineering. So yes, we can get there. Yes, we can do this. Part of it is deciding that we are going to do it. So where might we be going? Okay, where might we be at the end of this century? So I would suggest that what needs to happen is that certainly, we don't need compiler control. Right? You shouldn't have to have a license to get a compiler or something like that. I'm not suggesting anything as radical as that. It's making it illegal to program without a license. If you want to write a program to make your model trains go, or to play Flappy Bird or something like that, and fine. Certainly, there should always be software hobbyists. There's nothing wrong with that. But if you want to build safety critical, mission critical software, then what we need is to have a true self-regulated profession. We need to develop some set of materials. And yeah, I know we tried this once before with the whole object-oriented programming thing, and that was supposed to result in reusable materials that would be snapped together, and that didn't quite work out that way. But that doesn't mean that the vision was no good. It just means that it didn't work the last time we tried it. Excuse me. We need better modeling. We need to be able to have math that allows us to mathematically model behavior beyond just network performance. Yes, we need standards. The standards will be fallible. They will not be perfect first thing out of the box, but as long as we include some way of refining those standards, of improving those standards over time, then they'll be self-correcting. Anything that's wrong in them will get fixed. And as I said, we need some sort of self-regulation. We need certifications, and government needs to recognize those and say, look, you want to work on this project, you need to hold these particular certificates. And as I said, we are getting there, slowly but surely. So I think that actual piece of how we get to the engineering state is something that's happening. So we've come a long way. I mean, we've been 60 years and gone from software being this kind of curiosity to software being central in pretty much everything we do. So certainly it's useful. It's hard to imagine life without it, but we still have some distance to go. Now, excuse me, some people might say, no, it's kind of frustrating, but I would say actually this is a great time to be in software engineering field because we are figuring stuff out. See, if we knew it all already, it'd be less interesting, less challenging. Like, I'm not saying that it wouldn't be interesting to be a civil engineer, for example. Certainly, sense of achievement in building some physical object that you can see. But for the most part, it's figured out. The math, the science, the technology, they're figured out. And so, yeah, it's good that it's figured out. But think of it this way. As software engineers now, we get to be the people that actually invent the profession. So it's an exciting time to be a software engineer, to be part of the people that are the founders, if you will, of this profession. We need to start thinking about it more seriously, like how we make that transformation, how we move to true engineering. I think we've been way too stuck on process wars in the last 10, 15 years. Of just way too much battle and fighting about, this process, that process. Process is great, pick your process. Obviously, following a good process is part of good engineering too, but that by itself is not the solution. And skills, skills are really important. Obviously, we want to make sure that everybody involved in building software, at least software that matters, has the right skills. But we have to understand that process and skills, that's craft stuff. And we need to say, okay, yes, the process is good, skills are good, but how do we get the science, the math, and the engineering materials in place that will allow us to actually progress to being true engineers? So, people who are leaders in this profession really do need to say, enough with the process wars. Let's say, we know we've focused enough on process. What do we need to do to move us towards true engineering? And if we do that, when we focus on that, then I think that by the end of this century, we will have progressed to where aeronautical engineering got and beyond in this 150 years. Okay, so put the advertisement up, and we'll go into Q&A mode here. Let's see. So I got a question here or comment here from Bill saying, moments after your Roman aqueduct slide failed, my PC failed. I just rejoined after a reboot. Huh. Well, interesting. I don't know. I'm not sure what you guys saw when that failed. What I saw was my interface just disappeared. And it's like, okay. I mean, the GoToWebinar interface, it just blanked out. I'm not sure where exactly it went. It was somewhat irritating. But anyway, looks like very few people had a problem. So let's see. Got a question here. Diego asks, in terms of what would you apply math to represent functional software behavior? Well, I don't know for sure, Diego. That's part of the puzzle. If I knew that, then then we'd start to have it. But I guess my point is, if you look at other professions, they have a lot of mathematical models that they're able to use. As I said, you've got, well, for electrical engineering, for example, you've got all sorts of math that allows you to understand the behavior of electricity in different kinds of materials. There's, all kinds of mathematical formulas around that. Aeronautical engineering, you have math that describes how airflows work. You have Bernoulli's law and so forth. You've got, in every other form of engineering, there's math that describes how things behave, and we don't have that. And that strikes me as a problem. Now, you could say that you can't really have that because software doesn't it doesn't exist in the real world. It's not physical. And okay, yeah, I get that. And there's also the issue of what's called computability, which is like, if you can't create a program that's able to predict the behavior of every other program that could possibly be written. So I get that there are limits to what we're going to be able to do with the math. But it just strikes me as right now the software engineering as a profession is deficient with respect to math compared to other fields of engineering. David asks, I got here late, but I didn't see any mention of the NCEES PE exam for software engineering. I didn't want to get into the specifics of where engineering licensure is for different states right now for software engineering. I know there is some progress being made there, slowly but surely. But my main point is that that's part of the licensure certification. That's part of the mix, and we're not there yet to the extent that we are, say, with other forms of engineering. But we're getting there. Alex says, great webinar, Rex. Thank you. I've had this conversation with several colleagues in the past. The main argument from them is the fact that when you plan to build a house or a bridge, the requirements don't change on a weekly or daily basis. In software development, especially these days, due to market demands, the requirements change weekly, as something that the clients wanted last week may no longer be valid. How to apply civil mechanical engineering principles in an ever-changing market that we live in today? Well, I mean, that's a good point. I get that point. And sure, you know, now you've got, excuse me, now you've got with agile methodologies a process that allows you to let that happen, to let that change occur. But that by itself isn't enough. And, you know, I think you see examples of large complex systems that if you let the requirements change all the time, bad things happen. So healthcare.gov is an example of that. That the requirements for whatever reason, and leaving aside the politics of it, the requirements for that were not nailed down until, you know, just a matter of months before the thing was going to be launched. And that just didn't leave anywhere near enough time for the kind of testing that needed to happen at the end of that process to make sure that everything talked to everything else. You know, so I think you can say, yeah, there's stuff that can be built in a way that it just sort of evolves over time, but there's also stuff where that approach, even if you're using an incremental approach to building things, you can't just say, we're just going to make this stuff up as we go along. And even if you look at say, Scrum, for example, there is supposed to be a release backlog that is defined when the project starts that says this is in general what we're trying to build, right? And I guess what I'm saying is that there are going to be certain kinds of systems where you're going to need to do some fairly sophisticated upfront design work to figure out what the software is going to look like and how it's going to work if you want it to actually work. I mean, I don't think you want we'll figure it out as we go along approach to building software that runs the controls airplanes. You know, I just don't think that that's something that's that's a tolerable approach. So, yeah, you know, having a process that will accommodate change in situations where things are going to change over time, sure, that's great, that's fine. But, you know, again, I just think, as I said in the presentation, that there's just been too much silver bullet mythology around process on both sides of the debate, on the CMMI side of the debate and on the Agile side of the debate. Just too much, you know, process is going to solve all of our problems. No, process is going to help you organize your work. And if you follow a good process, then your work will be more organized. But it's not. It doesn't make something into engineering. Let's see. So Doug has a question here. I have 15 plus years in software testing across a large variety of disciplines. However, I have never obtained a certification for my craft. Most employers don't recognize certs. And the typical opinion is the skills are what people want versus the piece of paper. If paper certifications become the requirement, then I can see a lot of current working professionals will be pushed to the side. Any comments on this paradigm? Well, as to the question of whether employers recognize certifications, it is becoming more and more widely recognized. Now, it is important that people understand what the certification says. You know, I think that there are way too many people who just say, "Oh, well, I got my foundation certification from ISTQB, and therefore there's nothing else that I need to know as a tester," right? And I think there is some amount, because I hear about this, some amount of laziness on the part of hiring managers who just go, "Oh, well, you know, if I hire only certified people, then I don't have to worry about what their skills are." and they just look at the foundation and go, that's good enough. And then the foundation is the ISTQB program. The foundation is just exactly that. It's an entry-level certificate designed to give people basic concepts. It is by no means saying, oh, yeah, look, this person is perfectly qualified to be a senior tester. It's not intended for that. That's the advanced and the experts are intended to say that, these are people who have really mastered what they're doing. Now, as far as people being pushed to the side, if somebody refuses on principle to get certified, they say, this is evil and bad and I'm not going to do it, then it is already the case that that person is going to be excluded from certain jobs, because there are certain organizations, more and more of them over time, that will only hire people who have certificates. Now, they're doing this right. As I said, they're not just looking at the certificates. They're also looking at what other skills and experience the person brings to the job. But, yes, you limit your job choices if you refuse to get certified. Will people get shaken out of the field that way? Again, I think it's only by choice if they do that. Using the engineering analogy, were there people who were practicing engineers in the early 1900s that, as licensure became a requirement, they got pushed out of the field? Yeah, probably so, and depending on how difficult it was to get the license. And I'm not advocating that we go back to a guild kind of thing where, we create situations that limit the supply of software engineering and software testing professionals in order to jack up our rates. That wouldn't work anyway, but I'm certainly not trying to do that. But I do think that we need to get to a point where somebody gets on an airplane and they know that the airplane is controlled by software to a large part, that they can have confidence that things were done properly with respect to building and testing that software. I mean, let's take this Snowden case for an example, right? I mean, some of you listened to me before on some of these webinars will have heard me bang this particular gong, but I'm going to bang it again anyway. Here you got a guy who is a high school dropout. I don't know what his qualifications were for getting in as a network administrator at the NSA. Somehow or another, though, he does manage to get in there, and the security controls are so shoddily constructed that this guy single-handedly manages to pilfer incredible amounts of very sensitive information. Now, some people have said, "Oh, Snowden's a hero because he exposed all this stuff," and other people have said he's a traitor and should be hung. I don't want to get into the politics of it, but the competence or incompetence is really the issue I'm driving at. The incompetence of the NSA software system administrators, network administrators, and so forth, the security people, to have set up a system that is so easily penetrated by a single person to such an incredible degree is mind-boggling. The incompetence associated with Bradley Manning being able to do a similar kind of mass data swipe in Iraq and get that out. There's a competence problem in terms of how those networks were being administered, and that's not confidence inspiring, I guess, is my point. So, I would say we got to be smarter than that. As a profession, we've got to be smarter than that. Rajesh says, how would you suggest applying engineering principles to software testing? Well, I think part of that is we are seeing more application of modeling to the development of tests. So, for example, the construction of state diagrams, decision tables, identification of boundary value analysis, boundary values, domain analyses, and you know, we are seeing more and more use of modeling. So I think that's part of it. Performance testing side, there's definitely a lot of good modeling work that is done there in terms of modeling of performance. So I think you're starting to see it emerge. Now, these things, they kind of build one upon the other. And so this does bring us back to skills. And I'd say that process and skills alone are not enough, but certainly skills are a big deal. They're an essential component of having true engineering. So people need to learn these different modeling techniques and put them in practice in their daily work, and just start building on them. So we need to see a greater dispersal, if you will, of these kinds of skills. And it's remarkable, that you could still go in and find people who they're paid to be testers, and you could give them a description of an input field and ask them to apply equivalence partitioning to designing a set of tests for that input field, and a large number of testers, people who get paid to do testing, could not do that right. That's a technique that has been around since Glenford Meyer's book, The Art of Software Testing. So there's definitely a big skills deficit there. So people need to just work on developing those skills. Diego, a follow-up question here. He says, "Thanks for your answer, Rex. Very interesting. Could you explain how you apply modeling to performance testing?" Well, basically, the way this works is that there are tools out there that will allow you to build a model of the network, a description of the network. And the one that I've seen is called Hyperformix, but there are others. Shunra, for example, I think makes one. You build a model of the network. Excuse me. Build a model of the network, and then you're able to do statistical simulation of how that is going to behave under certain levels of load. And you can check the model up against your test results. So you run actual tests, and you can check them to make sure that the model is correctly predicting the behavior that you're going to see. And that can be a very powerful technique. I've seen that used to avoid some real performance-related disasters on some software projects. Lila asks, if math becomes a part of software development, how do you think a test analyst will need to be positioned in order to ensure quality? That's an interesting question. I guess it depends on where the math gets glued in, if you will, where it actually gets inserted into the process. If it's primarily on the development side, then maybe it's less of an issue for testing. But ideally, it would be both. Would be on both sides, testing and development. In which case, part of what you would have to do as a tester is be able to analyze the math that was behind what was going on and say, oh yes, that's correct or that's incorrect, or you've forgotten a situation in which the math doesn't work, and so it's going to break down here. So yeah, it could lead to a more rigorous form of education for software engineers and for software testers, where there's a lot more focus on understanding the math. And I can't really predict how this is going to play out. And really, what I'm looking at here, what I'm talking about, this is an analogy. I'm saying that we can learn from these other forms of engineering. What exactly that will look like, I don't know. But there are certainly lessons to be learned there. A comment here from David regarding the math. The body of knowledge for the CSDP certification includes mathematical foundations. So apparently that is, people are starting to think of that as important. Nico says a comment here on the what happened when the little glitch. He says, I show your presentation in edit mode. It was like you hit the escape button on your keyboard by mistake. Nothing weird. Great presentation, Rex, as always. Thank you. Yeah, it was just kind of disconcerting to me because the GoToWebinar control interface disappeared, and it looked like it had that the GoToWebinar had crashed, which kind of panicked me because I was like, oh, I wonder if this has ended the webinar for everybody. But somehow or another, it got hidden behind other stuff, and I had to take us a minute to dig it out. So Roy has a comment here. I'm assuming that Roy, you must be from the UK because of what you write here. Software probably has the most amount of maths. That being the maths part is how I'm guessing that you're from the UK, because you guys call it maths and we would call it math. Okay. Computer science was derived from maths. I think we are pretty well covered for maths. What maths do you think is still required? Well, okay, fair comment. Yes, there was certainly a lot of that in my computer science education at UCLA. But I don't, I can't say what's missing. It just seems like in day-to-day practice. So I know people who are in other engineering fields. My father was a civil engineer, for example, and it just strikes me that in their day-to-day practice, they're using math a lot more. And other than performance modeling and certain, forms of test design, it seems like we just don't use it as much. It just feels to me like there's a deficit here. And again, I'm making an analogy here, Roy. You don't want to take it too far, but I just think that by comparison to other engineering fields, if you look at what they've got in their day-to-day practice and what we've got, it seems like math is something that's just more prevalent in the other forms of engineering. So Armin says, I was late, so sorry if you already mentioned it. What about IBM efforts many years ago regarding the software clean room? I believe there were mathematical proofs of correctness, etc. Yeah, I mean, I remember studying that idea of proofs of correctness, where basically you are doing math. I seem to remember it being somewhat controversial as to whether or not that would that could actually be generally applied, and it didn't really go anywhere. Now maybe that's still in use, but I certainly haven't run into it with any of my clients where they're sitting down and doing proof of correctness. Now maybe there are companies out there that are using it, and it's so successful to them that they don't need a testing consultant to come in and talk to them about testing. So maybe that's why I haven't seen any of it. But yeah, I mean, I think to your general point, there have been occasional efforts to introduce that kind of math and that kind of rigor. So we'll see where that ends up. I think in any form of engineering, in the early times of it, there's going to be trial and error, right? And so, at this point, as the software engineering profession matures, we are trying a lot of stuff and seeing what works and what doesn't. Doug says, thank you. Great response to a long question concern. You're welcome. Let's see. Freddie, interesting webinar. Do you predict that testing will eventually become a profession based on engineering alone, or will there be a need for craftsmanship in testing? Some folks heard me give this presentation in Helsinki back, whatever it was, last summer. And I think they misinterpreted what I said to mean that, attributes that you would associate with craftsmanship, pride of work, creativity, those sort of things. I'm not saying that those are bad. Those kinds of things, pride of work and creativity and such, are present in true engineering. So engineering done right has what crafts have, but more. They have, as I say, the engineering materials, the math, and the science. So I'm not saying throw away the parts of craftsmanship that make software engineering what it is today. I'm saying don't accept that as enough by itself, that we need to go beyond that. We need to build up beyond that point. So I'm not denigrating the positive aspects of craftsmanship, and I think that's always going to be something that's necessary. Comment from Diego. Thank you again. You're welcome. Rajesh says, thank you very much, Rex. You're welcome. So we've gotten through the questions. Seeing that we have no further questions, I'll just close the session down. I'll tell you a little bit more about the resources available through RBCS. We run these free webinars once a month, so check our website to sign up. Special webinar presentation of this webinar or any other webinars are available. Send an email to info@rbcs-us.com. Sign up for our free newsletter at rbcs-us.com. We've got a great guest article by Jim Copleen coming out this month. He makes some very interesting and potentially controversial points about testing and unit testing specifically, but also testing in general. So I think you'll find that very interesting. So we have that newsletter comes out every other month. You also get valuable discounts, news about what we're doing. You can follow us on Twitter at twitter.com/RBCS, and we're also on Facebook at RBCS-INC. Do remember to check your email over the next couple days. You might be the lucky winner of a free e-learning course from RBCS. You will register for a random drawing for such a course simply by attending this free event. Make sure you check out our digital library. If you think somebody needs to listen to these webinars, they're all recorded out there along with a bunch of other videos. You can subscribe to our podcasts. It's available on iTunes, and also it's RSS feed out on our website that will allow you to download those on a regular basis. Some people are wondering, do we is this time change permanent? No, we're gonna revert back to the normal time starting the next month. We just had to do this time change here because of a schedule conflict with a risk-based testing virtual course that is happening Tuesday through Thursday. So those of you who found this time a little inconvenient, for example, if you're on the West Coast, apologies for that. We are going back to the normal time next time. Also, a question sometimes come up about the PMI PDUs. You will get an email that will tell you how to claim those. That will come out in the next 2 or 3 days. So we offer these free resources as a service to the software testing community because at RBCS we are a not just-for-profit company. Concludes the webinar. Thanks for joining us.